Hello? Does it work? Okay. So in this project, we proposed an efficient spectral algorithm for HDP. And so first of all, I will talk about HDP, and then Fish will describe our algorithms in details, and then we will show some experiment results. So let's start from DP mixture models. So in DP mixture models, it's an infinite model, and that each G samples from alpha 0 and G0 from the derivative process. And then for each data, we have a parameter theta I sampled from G, and use this theta I to generate some data X. And however, in this infinite model, the mixing components are not shared because the G0 is continuous. So in many applications like topic modeling, we usually want the mixing components can be shared across groups. So in HDP mixture models, we have this model, and we have another layer G0 sampled from H. So now the G0 is discrete. So now the Gj can share some mixing components across groups. And this is very widely used in many applications, such as topic modeling. However, when doing inference, people usually see HDP as Chinese restaurant franchise, which is very similar to Chinese restaurant process, but with hierarchy. And also apply the Gibbs sampling for the inference, but it's usually computationally expensive. So that's the reason why we want to propose a new spectral algorithm for this model. Okay.
So our idea is that we can use method of moments. This is a simple example that we will learn in our statistical class. Is if some samples are drawn from Gaussian, it's easy that we can derive mean and covariance and recover these parameters. So now we are going to derive the moments for HDP. That's review of the notation. So X is a word in the document. So this H will generate a topic, a global topic. It's potentially infinite, but we know that sound of topic will will have more obvious performance than others. So we can assume that we will have k largest number of Latin topics. And then each document will generate their own topics, like some of the documents is talking about sports and pets, and another one is talking about health. So the health topic will have larger magnitude on the topic probability. So X is a word in a document. So X is the observation, and only one of the element is 1. And K is the number of Latin topics, and O is the word distribution for each topic that we inferred. And H is, here we need to notice that H without the J on top of that is global probability of topics. And H with a J on it means the J's document is the J's group. So for the first one, it's simple. If we calculate the probability of each word appearing in these documents, then it will be OH. H is a global topic. And you will ask, how do we get K? We can see that for each document, we can calculate its mean. And this mean is spanned by the space of O. So we can just check this matrix. It is consisting of the mean of every document and see what's the rank of this matrix. And do we lose other constraint in this model? Yes, it's because this H1 to Hk is generated from a Dirichlet distribution. So we will have the sum of Hi is 1 and also a Dirichlet distribution for them. This is for the local case. It's the same, but we have to notice that the alpha parameter is derived by the global topics. So it will be alpha multiplies H. Before we start to derive the second and the third order moments, we first introduce this notation. We will call it cross here. So cross means that if we have p vectors and we cross them together, it will become a p-dimensional structure. So like if we have two vectors cross them together, it becomes a matrix. And if we have three vectors cross them together, then we will get a cube. So then we start to derive our second order moments. We first write them up. And here we have to know that x1, x2 means word 1 and word 2, or word 1 and word 3. So we multiply every possibility together, and it's within a document, not across. Because in the same document, we will have the same hidden Hj. So here for the first order moments, we can calculate the expectation over H by Dirichlet distribution. And then we will find that it is actually alpha over alpha 0. Alpha over alpha 0 is a vector. And for the second order moments, we can calculate the expectation over each groups, and within each group, we can separate them to two parts. So here, you can just plug in H1 squared to the distribution and derive the diagonal coefficient here. And for the rest, it's like that. So if you examine this carefully, you can find that it is exactly equals to the what I wrote on the button. So we will have S1 and S2. Here I have to say that S stands for symmetric and spectral, and M stands for moments. So be careful of the notation. And for the third one, we can find this. We can following the same tricks. Is that we will first multiply S1 together and get a cube, and then we do some elimination on the diagonal, and then do some compensation on the qubit diagonal. So after we derive all this, we can see that this structure is like eigenvalue and eigenvectors in matrix. So here our problem becomes that we are trying to find the eigenvector and eigenvalues for a cube. And how we get that is by tensor decomposition. It's a paper by Anima Adekumar. Here we will define the tensor that have k eigenvalue and eigenvector. And if a symmetric tensor can be represented by this, we will call it a p-rank tensor. It's similar in the case of matrix, if we say a matrix is a P-rank matrix, then we can find k eigenvalues and k eigenvector, and then sum them together. So we will solve this by the basic idea of Riemann quotients is, in metric case, we will arbitrarily generate a random eigenvector. We assume that this is our eigenvector. So we will update them by this equation, and then iteratively it will converge to our desired eigenvalue and eigenvector. So the whole algorithm is something like this. So we will randomly generate some of eigenvectors and then update them by that. And finally, through several iterations, it will converge to our desired eigenvalue and eigenvector. And another thing to mention is we need to do exact correlation analysis, is because the latent features might not be orthogonal. Because when we are deriving those eigenvectors, we are assuming they are orthogonal. So the idea is to use S2 and find a W that whiten these latent features. Okay, so W is derived by, for S2, we can do singular decomposition and then find W by eigenvectors multiplies the eigenvalues. So our algorithm is basically like this. We calculate S1 and S2 by the moments, and then do whitening on these tensors, and then we use tensor decomposition to derive eigenvalue and eigenvector, and then reconstruct them by multiply a pseudo transpose W. So after that, we will get K and we got O, so we still need to get H and Hj. And this can be done by projecting the mean of each document on the O we derived. So this algorithm is actually very fast because we only do SVD on a K times K matrix. And also for tensor decomposition, we can use kernel trick to make it done by linear time. And we also derive some of concentration of major for this to have a guaranteed bond, but I think we don't have time here to explain this. So we will go to our experiment results.
Yes, and we test our algorithm on around 1,700 data and implement it in MATLAB. And this is the topics we recovered. It is, we can get some meaningful topics. And the computational time is a lot faster. It takes only like 500 seconds compared with the implementation by EYT. Their code costs like 30 minutes per iteration on our machine. So it's a lot faster. And so, yeah, to sum up, we have proposed an algorithm that can effectively estimate the parameters in HTTP mixture models, and it's much faster. And of course, to better evaluate this algorithm, we also have to do the perplexity analysis. But the perplexity analysis on the Gibbs sampling one takes some time, so we'll report the results on our final report. And also in the future, we can also extend this to deeper hierarchies. So yeah, thank you. Yes?
So you just had to calculate 3 movements?
Yes.
Which I find very interesting because HMM also needs 3 movements, and this model is, or also I think Anima's paper does, for MMSB also there are 3 movements, and you just need 3 movements for HTTP, which is
Oh, we actually use 3 moments, right?
We need the third order moments for this.
Third order moment.
Yes, because you can see that maybe you can do eigen decomposition on S2. That means the spectral structure for the second order, but actually tensor decomposition will do better on a third order moment or higher order
So
moment.
do you need higher than 3 or just 3 would suffice?
3 is sufficient. Yes. So anyone has another question?
I have a question on the
okay.
experiment. You described the computational improvement, which is significant, but how about accuracy? Do you also compare to, say, the accuracy is comparable or it's even better?
Yeah, so we want to compare the accuracy by the perplexity
Oh,
analysis.
that's what perplexity.
Yeah, it's like likelihood.
Okay.
Yeah, so if our algorithm can provide something similar at likelihood, yeah, that means, yeah, maybe this is correct.
But then, sorry about
But what does likelihood correspond to the
Oh,
quality of the actual solution?
it's still running because the code for give sampling takes some time. So, yeah, we will report the results in our final report.
Sure.
Yes, thanks.
But then, like, isn't spectral method supposed to give you global optimas because they are using a signal? So I would presume that they would perform better. If I
Mm. Yeah.
Spectral methods like avoid optimal, but not of the same objective. They change the objective function.
I see.
Yes.
Okay.
So you mentioned that you could do a tensor decomposition in linear time using the kernel kit. Is there a reference for that? Can you go back in the slide?
Okay.
I think it's in linear.
I know, but you can see this tensor decomposition. Actually, the time is decided by the iteration we set for L and S here. Yes, because calculating this, we only need to calculate the inner product of 2 vector because we can reduce the dimension by some kernel trick. Yes.
How do you ensure orthogonality of your eigenvectors in the tensor decomposition? Because you assume that a tensor can be decomposed into that orthogonal expansion.
Mm-hmm.
I'm assuming somebody proved that, I don't believe it right away, but suppose that decomposition exists. While doing numerical computations, orthogonality is very difficult to ensure.
Mm-hmm.
And did you implement your own version of the whole decomposition, or you downloaded somebody's code?
No, we implement by ourselves. And how we check this is we can generate a known the data features and then see if we can recover that by this.
I was just talking about the numerical algebra part of it. That in your decomposition, the things that you're calling the eigenvectors of your tensor, you're also assuming they're orthogonal.
Yes.
Are you able to numerically construct orthogonal vectors? Or it doesn't matter for you?
But we do whitening here. Yeah, we do whitening, so it doesn't affect. It doesn't affect it in this case.
That's what the transform makes some vector.
Yeah, the thing is, all of these things become fairly delicate. Getting orthogonal eigenvectors is not an easy job, even for matrices, actually, regardless of what you do. But anyhow, that's a side point that orthogonality is a difficult thing to achieve. But K is small, so it's okay.
Mm-hmm.
And is there a proof that that iteration converges to the desired?
Uh,
Like the
we have guaranteed bound, and also a small experiment proved that this work.
Okay, thank you.